Chain reactions. Specification point 7.20. Describe how a chain reaction can be set up if the neutrons produced by one fission strike other U-235 nuclei. A nuclear chain reaction occurs when one single nuclear reaction causes an average of one or more subsequent nuclear reactions, thus leading to the possibility of a self-propagating series of these reactions. The specific nuclear reaction may be the fission of heavy isotopes, for example, uranium-235, 235U. Nuclear chain reactions are reactions where nuclear energy is obtained, generally through nuclear fission. These chain reactions are what provide nuclear power plants with the energy that is then turned into electricity for use by people. In these reactions, neutrons generated by the fission process continue on to initiate fission in other atoms. These reactions generally occur with heavier isotopes such as uranium-235 where there are a continuous release and absorption of neutrons. Figure 1 below is a visual representation of what a nuclear fission chain reaction looks like. If at least one neutron from each fission strikes another U-235 nucleus and initiates fission, the chain reaction is sustained and it is said to be critical. The mass of uranium-235 that is required to produce a reaction that is self-sustaining is said to be the critical mass. This critical chain reaction can be accomplished at relatively low uranium-235 concentrations if the neutrons are moderated to lower their speed. A moderator is necessary because the probability for fission is greater with slow neutrons. The general equation for a nuclear chain reaction of uranium-235 is: if every one neutron inputted into the equation releases 2 or 3 more neutrons, then the number of fission events increases dramatically each generation. However, in reality, not all of the released neutrons actually cause more fissions. Only one neutron per reaction actually goes on to cause more fissions and continue the chain. However, the number of fission events still grows quickly. The process of a nuclear chain reaction releases large amounts of energy. In the fission reaction, a slow-moving neutron is absorbed by a nucleus of uranium-235. Figure 25.11 example of fission of uranium-235. The resulting uranium-236 is unstable and splits apart. The fragments of this decay are the 2 daughter nuclei of barium-144 and neutrons. The decay also produces gamma radiation and 3 more neutrons. The equation for this decay is uranium-236 barium-141 plus krypton-91 plus 3 neutron plus gamma radiation. The fission reaction produces a huge amount of energy. This is because the mass of the products, the barium and krypton nuclei, and the 3 neutrons, is slightly less than that of the original uranium-236 nuclei. This lost mass is converted to energy. Most of the energy is carried away as the kinetic energy of the 2 lighter nuclei. Some are emitted as gamma radiation. The 3 neutrons produced by the fission may hit other nuclei of uranium-235, so causing the process to repeat, as shown in figure 25.2. If one neutron from each fission causes one nearby uranium-235 to split, then the fission reaction will keep going. If more than one neutron from each fission causes fission in surrounding nuclei, then the reaction gets faster and faster, a bit like an avalanche. This is called a chain reaction. Each fission results in more nuclei splitting apart. If the amount of uranium-235 is small, many of the neutrons released do not hit other uranium to happen. There must be a minimum amount of the uranium-235. This minimum amount is called the critical mass. In an atomic bomb, 2 pieces of fissile material, isotopes that can be triggered into splitting apart, that are smaller than the critical mass are forced together under high pressure to form a mass greater than the critical mass. The result is a chain reaction with the rapid and uncontrolled release of huge amounts of energy. Figure 25.2 A chain reaction in uranium-235. If this is allowed to take place in a nuclear reactor, the reactor core overheats, resulting in a nuclear explosion with the sudden release of enormous amounts of heat energy and radiation. In a nuclear reactor, the process is controlled so that the heat energy is released over a longer is used to heat water. The steam produced then drives turbines, engines, to turn generators.